The next topic we're going to go over is measures of spread. And spread you can think of as how far apart are your data values. Just to give you an idea, these data values you could think of as being pretty far apart, a large spread, and these data values you could think of as being fairly close together, a small spread. One of the definitions we'll need to measure spread is deviation. And formally, deviation is an observation minus the mean. It's the distance from the mean to a number. Just to give you a visual, let's say that this is the mean of your data set, the average. Well, if this is an observation, and let's just call it our first observation, if you do x minus mu, smaller minus larger, you're going to end up with a negative deviation. And let's say that this is a second observation. And if you do x minus mu, larger minus smaller, you're going to end up with a positive deviation. So one of the issues we're running into is that if your observation is larger than the mean, you'll get a positive deviation, but if your observation is smaller than the mean, you'll get a negative deviation. We have three measures of spread, or deviation, or variation. The first one would be the range, which is maximum minus minimum. Going back to our notation, that's x parentheses n minus x parentheses 1. The second one would be the variance, and for the population, this is sigma squared, and for the sample, this is s squared. And then there's standard deviation. For the population, it's sigma, and for the sample, it's s. And just to throw this into a diagram to help you keep it all organized, if this is your population, remember this is all observations. We come in, take a simple random sample, and get our sample. So you have your mean, your variance, and your standard deviation all falling into the population. And then again, a mean, a variance, and a standard deviation falling into the sample. Just different notation for the cases. These numbers are what we call parameters for the population. They're numbers that describe the population, and these numbers are what we call statistics. They're numbers that describe the sample. We're going to start out with variance and look at the formula for variance. By definition, variance is the average square distance from the mean, and its units are the same units as the original data set but squared. Population variance is represented by the sigma squared, and this is its formula. The sample variance is represented by s squared, and this is its formula. Notice the difference in the formulas is that population uses a mu, and sample uses an x bar. The standard deviation would be the square root of the variance, and its units will match the original data sets. For the population, this is the formula. And for the sample, this is the formula. So the first says, take the square root of the sum of x minus mu squared over n minus 1. And the sample standard deviation says s equals the square root of the sum of x minus, and this symbol got a little messy, x bar squared divided by n minus 1. And just so you know, sometimes the standard deviation can be approximated by the range divided by 6. So here's an example. We have two data sets, and we want to go through and compare them and see what's the same and what's different between these data sets. Let's start out by plotting them out. So I'm going to create a dot plot for each of these. So I have my number line, and for data set 1, I'm going to put points for the 1s, a point for 4, and points for 7. If you thought of fitting a smooth curve over this, it would have a shape that roughly comes out like this. And now let's do the same thing for data set 2. Number line. And mapping out my points, I have 1, 3, 4, 4, 4, 5, and 7. And again, think of fitting a smooth curve. If you were to describe the shapes of these curves, for data set 1, we would say that this is bimodal. And for data set 2, we would say that this is symmetric and bell-shaped. So let's see if we can get numbers that help describe the difference in these two data sets. And just for spacing, I'm going to have to erase out these dot plots, but I'll draw the general shapes next to each data set. So the first way we can compare these is with measures of center. And I'll go through the mean and the median. For data set 1, you would add up your ordered observations. And then divide by the number in the sample space. Here there's 7 numbers. So if you add these up and divide, you'll find that your average is 4. There's 7 observations here, so the formula for your median, since 7 is odd, is n plus 1 divided by 2. 7 plus 1 is 8, and 8 divided by 2 is 4. This does go to your 4th ordered observation. So here's my 1st, 2nd, 3rd, 4th. And in this case, my 4th ordered observation just happens to be the number 4. So in this case, the mean and the median fall at 4. The center is right here at 4. So just to summarize, we have that the average is 4 and we have the median is 4. If you repeat these procedures for data set 2, you'll find again that the average is 4 and the median is 4 for data set 2, and that the center falls about right here. So the measure of center isn't describing a difference between these two data sets. Let's see if we could get a measure of spread to describe it. So one measure of spread would be the range, which is your maximum minus your minimum. Here the range is 6. And if you come over to data set 2, maximum minus minimum, your range is 6. So this measure of spread doesn't describe a difference. Well, let's go to our next one. Let's try a variance. I'm going to work on finding the variance for data set 1, and I want to try and show you a visual of what's going on. So I've redrawn the dot plot for data set 1, and I want to come in here and label that the center is right here at 4. The variance is the average distance from center. So what I could do is get the deviation, the distance. And here, remember, deviation is x minus mean, and our mean here is 4. So 1 minus 4 gives us a deviation of -3. And again, I could get the deviation here and deviation here. This observation, 4 minus 4, gives us a deviation of 0. And then I could come in and get the deviation on this end. Observation 7 minus mean 4 gives us a deviation of +3. So if I were to add these deviations up, it turns out that they sum to 0. Your positive and your negative deviations cancel each other out. This is saying the average distance from the mean is 0, which is impossible, because to be a distance of 0, your numbers would have to fall like this, which they clearly don't. So the way that we're going to handle this is to, instead of thinking of it as a average distance, we're going to think of it as an average squared distance. So all these deviations, we're going to come in and throw squares on them. And squaring will get rid of the negative numbers so that we're only adding up positive deviations. And this time when you add them up, you get back 56. There are no positives and negatives to cancel each other out because we've squared the deviations. Now, this isn't quite the full answer because we now have the total deviation, but what we're after is the average deviation. So to get by the average, we have to divide by the amount of numbers we added. Here, we're going to take 56 and divide by the 1, 2, 3, 4, 5, 6, 7 numbers that we added, with a slight twist. The formula says divide by that number minus 1. So we're really looking for 56 divided by 6, and that is 9. So in this case, the variance, or S squared, equals 9. So just to summarize this for data set 1, we have the S squared is 9, and this is your variance. And to get your standard deviation, you take the square root of 9, which is 3, and this, again, is your standard deviation. Now I'll go ahead and tell you that if you repeat these steps for data set 2, you'll find that your variance, or S squared, is 3.24, and your standard deviation is 1.8. And I'm also going to go ahead and add in the shapes of our distributions. So the thing that you should notice is that in data set 1, from the center, most of your points are pretty far spread out. And the variance and standard deviation here were fairly large, 9 and 3. Whereas in data set 2, most of your observations are close to the center. They're centered about the mean of 4. And your standard deviation here is 3.24 and 1.8. So they're smaller when the values are close to the center. So when do we use each measure of spread? The range is used for small data sets, and outliers affect the range. The variance is used for small or large data sets, provided the data is bell-shaped and symmetric. Outliers affect the variance, and it cannot be negative. Remember, your bell-shaped and symmetric distributions would look like this. The standard deviation is used for small or large data sets, again provided that it is bell-shaped and symmetric. Outliers also affect the standard deviation, and it cannot be negative. The standard deviation is 0 only when all answers are exactly the same. For instance, I could say, how many siblings do you have? Every single person would have to answer the exact same number of siblings. There can be no variability in the data. The chances of everyone giving back the exact same number of no variability are practically 0.